Bismillahirrahmanirrahim. Assalamu alaikum. So now let's talk about some of the simple properties of Brownian motion. So I'll put these without proof. Let's put them in the form of proposition. So for any time t, for any t, Brownian motion is normally distributed. We all know is normally distributed with mean 0, with expectation 0, and variance t. Similarly, for any t positive, let's say s and t positive, non-negative, we have expectation of b of s times b of t is equal to minimum of s comma t. So this is like Brownian motion is normally distributed with expectation 0 and variance t. So this is one property. I won't be going into the proof because it doesn't involve anything much. You just consider this b of t being equal to b of t minus b of 0, then you can see that this is increment, and then you can go towards the increment and take help from there, and you can prove this assertion. And similarly for this you need some algebra, but I'm not going into the detail right now. Second property is for fixed t naught, this new process defined by b tilde or b hat to be b of t plus t naught minus b of t naught. So this new process, this is also Brownian motion, provided that the b is Brownian. If b is Brownian, then this quantity is also Brownian. And this property is called, this second property is called translation invariance. Translation invariance. What does that mean? That means that if you have a Brownian motion and you are translating it, this is nothing but translation. So when you are translating it, it doesn't lose the originality of being Brownian motion. So even you translate it, despite it remains the Brownian motion. So the translation of Brownian motion in this way is also Brownian motion. So that's the second property that you should keep in head. We also have a third property. Let me list that as well, and it says that for any real number lambda, for any real number lambda positive, of course, this stochastic process b hat defined by b of lambda t by square root lambda is also, this one is also Brownian motion, provided that this one is Brownian. So you have a Brownian motion, and you're doing it what? You're scaling it basically with this factor. So you have a Brownian motion, you compute it at lambda t and you divide it by square root lambda. It is again a Brownian motion, and this property is known as, this third property is known as scaling invariance. scaling invariance. So you are scaling the Brownian motion, it is again, Brownian. So if you are scaling Brownian motion, it will remain Brownian motion. So scaled version of Brownian motion is a Brownian motion. So I'll end here. And in the next discussion, we are moving for defining hopefully Wiener integral. And by the way, one more remark: in some books, this beta of t sometimes they also represent this w of t. So there is no any much difference at this stage. I won't be going into that difference. So sometimes people also represent this Brownian as w. Thank you.